So what is a simple example? This is a simple example. This is a simple example. This is an. This is an minus 1, right? And there is no more term. That's okay. So let's call it degree 1 recurrence. And then this is linear, because if you look at this an minus 1, just a single term there. You do not multiply with an minus 2 or a minus 3. You do not have a square of this one. Is that okay? And then here, you are adding a certain function. So this function is just depending on n. So this is a particular example of a linear recurrence. Okay? Okay. So there are general ways to solve a linear recurrence. But here, if you look at this, for this example, particular example, so this is the recurrence relation. And to solve it particularly, we need to specify enough boundary condition. So if I don't tell you what is the value of A1, there is no meaning of this one. You cannot get the value of any A terms. But on the other hand, if it is of degree 1, if I give you one value, then you can get the whole sequence one by one. Is that okay? Okay. So the first way to solve a linear recurrence is by guessing. So this is called method 1. We do this by guessing. So how do we guess? Okay, so how do we guess? So first of all, how do we guess? Let me give you another example. This one, not easy to guess. This one is quadratic, difficult to guess. Let me do another example. So let's try this one. Let's try to solve a similar problem, but this time it is an is equal to plus an minus 1 is equal to 2n plus 1. And let's say this time a0 is equal to 1. Let's do this. Okay. Look at this example. So first of all, so let's check. So this is a linear recurrence. What is the reason? This is a relationship between an and all the past terms. And then each of these past terms, and also each of these an here, is of a single degree 1. Is that okay? Okay. So this is a linear recurrence. Okay. So first of all, let's guess. Okay, let's guess what is the value of an. What could that be? So when we do the guessing, let's make the problem simpler. Let's forget about this boundary condition at the beginning. Let's guess, how does the form of an look like? Okay. So if you ask me to guess, if it is 2n minus 1, then that will be great, right? If it is 2n minus 1, how would you guess? an plus an minus 1 turns out to be 2n minus 1. And then what you may observe is n plus n minus 1 is equal to 2n minus 1. So in that sense, let's try to guess an is equal to n in this case, right? Is that okay? But how about this one? 2n plus 1. Then what should we guess? Plus 1. Very good. So plus 1, right? Yeah, it works, right? an is equal to n plus 1. Okay, now we can look back at this part. Okay, now a0 is really equal to 1. Perfect. Then in that case, we solve this whole thing. Okay? Okay, but, well, you don't get a lucky day every time. Let's say this time I ask you to solve the same thing, but with this a0 set to a different number, 4. Then what should we do? Okay. Then what should we do? yeah, we have different boundary condition, we should have a different term. And you find that n plus 1 does not work now. And what happened or why? So first of all, we are going to take a look of what can go wrong. Okay, so so you see that n plus 1 works perfectly for the recurrence relation. But then if you combine this with the boundary condition, it doesn't work. Okay, it is not working because there in the whole world there are something we call it zeros. Okay, that is affecting our result. So the zeros that is affecting the result. What is meant by the zeros? So let's look at a very similar recurrence relation. This time let's call it hn plus hn minus 1 is equal to 0. Okay, let's look at this. This is a different recurrence, but I set 0 here. Now, just for this one, we will see that if you set hn is equal to minus 1 to the power n, then minus 1 to the power n plus minus 1 to the power n minus 1, it is always equal to 0, right? Is that okay? Actually, if I multiply any a, constant a there, it is still 0. Is that okay? So if I plug in a times minus 1 to the power n here, and then a times minus 1 to the power n minus 1 here, you get 0. Okay? You get 0. Is that okay? Then, you get 0. Then let's come back to this an. An is equal to n plus 1, works perfectly for this recurrence. But if I add hn there, if I add a times minus 1 to the power n there, this whole thing will also work here. Does that make sense? The reason n plus 1 part will combine this to n plus 1. This a times minus 1 n part will combine to make a 0. So if I'm using this an, the new an, instead of the original an, it still works. It still works. So it means that for this recurrence, any n plus 1 plus a times minus 1 to the power n will satisfy the first inequality. Is that okay? So what should we do? So we call this the general solution for this whole thing. n plus 1, this part, n plus 1, this part, we usually call this a particular solution. Particular. Particular solution that works for the recurrence relation, but then it is not general. The general part we should consider, this is the zeros that we should also consider. So once we have a particular solution and the way how zeros could look like, we get the whole thing. This whole thing, we call it a general solution. Is that okay? Now, general solution, it turns out that it will capture all the possible ways for the first recurrence to be satisfied. To get the correct solution when the boundary condition is given, then it is easy. We put in the case into this general formula and solve for the value of this big A. Once we solve it, then this will be a solution of the problem. Is that okay? Okay. So usually in the textbook we don't call it zeros, but the meaning is zeros. We call it. We have a different name for this one. This is called what? If you study the differential equation or whatever, then you have similar terms like particular solution, and this is called the homogeneous solution. Okay, so homogeneous means like everything looks the same. It means makes it look the same. So it's like 0. You add 0, it looks the same as before. Okay. Okay, and then for this particular example, how do we solve? So this is how AN could look like. So if I now tell you that A0 is equal to 4, then so we will have A0 is equal to 0 plus 1 plus A times minus 1 to the power 0. Is that okay? So that, what is A0? A0 is equal to 4 here. Is that okay? And then what do we get? So 4 is equal to 1 plus A. So we got A is equal to 3 in this case. Okay? Is that okay? So when A is equal to 3, then, okay, so for this particular problem, the solution will be like this. Okay? Is that okay? So here, this demonstrates one way of solving a recurrence relation. So first of all, we try to guess the particular solution and then find out the homogeneous solution. And then we combine the particular solution with the homogeneous solution to get the general solution. Once the general solution is obtained, we use the boundary condition to solve for the unknowns. So previously, we have an unknown big A. We solve for A is equal to 3, and then it works. Okay? Is that okay? Okay? And let's test. So maybe it's wrong, but let's test. Okay? So let's test our whether this formula fits. Okay? So we are claiming that AN is equal to what? So we have A0 is equal to 4, right? A0 is equal to 4. If you use the above thing, we have A1 plus A0 is equal to 3. So we will have A1 plus A0 is equal to 3. So we must have A1 is equal to minus 1. Am I correct? Okay. And then we have A2 plus A1 is equal to 5. So we must have A2 is equal to 6. Am I correct? And then we have A3 plus A2 is equal to 7. So we will have A3 is equal to 1. And then we have A4 plus A3 is equal to 9. Is that okay? So we must have A4 is equal to 8. It's something like this, right? Let's check. Let's check the formula whether AN is equal to n plus 1 plus 3 times minus 1 to the power n works. Okay? So when n is equal to 0, then we know that this is going to be 1 plus 3. So it works. So this is equal to 1 plus 3. So when n is equal to 1, then it is going to be 2 plus 3 times minus 1. 2 minus 1. So it is minus 1, so it works. Is that okay? When n is equal to 2, this will be going to be 3 plus 3. 3 plus 3 is equal to 6. It works. When n is equal to 3, then it is going to be 4 minus 3. So it is going to be 1. Is that okay? Is that okay? So each time it is either n plus 1 plus 3 or n plus 1 minus 3. Okay? So you skip. So if these two values is plus 2, then it is okay. If these two values is plus 2, then it is okay. So it works. Okay. Now what is amazing is that, so it looks like we are just doing some simple guessing and then doing the homogeneous solution, and they got something. And what is amazing is that if you get a solution in a way like this, then this is going to be the unique solution. there is no other general form solution that fits the recurrence relation. Now, to prove that it is unique is too difficult, okay, too tedious. But what we hope to deliver in the lecture is that this is one possible way of solving a linear recurrence, okay? Now, let's get back to a more difficult problem like this one. How do we guess? Okay. How do we guess? So let's try this one. How do we guess? So we hope to get a particular solution, right? We hope to get a particular solution. How do we guess? So first of all, an and an minus 1 is related to a function that has n there. So originally, the first thing that we may try to guess, this is the best way to guess, is let's try to guess an is in the form of some function an plus b. Is it okay? Does that make sense? Because if it is of the form an plus b, then maybe the difference is going to be a gain of some a prime n plus b prime, and then perhaps we can get to n minus 1 here. Does that make sense? Okay. But for this one, it doesn't work. Why? Does it work or does it not work? Let's try, okay? So if an is equal to an plus b, then what do we have? We will have an plus b is equal to a times n minus 1 plus b plus 2 times n minus 1. Am I correct? Right? Okay. B gone. Okay. Don't worry. B is gone. It's still okay. Problem. an is gone. Nothing's there. So we just have what? You just have minus a left and a 0 here. And then how do we solve this? There's no way to. So a is supposed to be a certain constant. B is supposed to be a certain constant, right? And there seems to be no way to have minus a plus 2n minus 1 is equal to 0. Because there's no n term there. Okay. So it seems that setting an to be equal to an plus b doesn't work that good. So what we can try next is, the reason is that if we simply set this to be an plus something, the an will be cancelled. Okay, so what can we do? We don't want to cancel it. So let's be a little bit clever. So we try the next power. So let's try an squared plus bn plus c to be this an. Okay, although it looks strange, but using one more power will be helpful, because in that sense, what do we have? In that sense, we will have an squared plus bn plus c is equal to a times n minus 1 squared. Wow, good, right? Plus b times n minus 1 plus c plus 2 times n minus 1. Is that okay? That's good, right? Suddenly, okay, so c can be gone. Okay, so c can be any number. So c doesn't matter. And then how about this bn minus 1 bn? Okay, so bn minus 1 and bn, then you have bn, so you have a b left here. Am I correct? Is it okay? How about this one? This is an squared. This is an minus 1 squared. So it is going to be what? A times 2n minus 1 left. Is it? Okay, so I will have, this is gone, so we have, okay, plus a times 2n minus 1. Is that okay? Okay, and then this is equal to 2n minus 1. This is equal to 2n minus 1. Is that okay? Then what do we get? Okay, so we can get what? So a is the only time that is going to multiply with n. So it must have a times 2n is equal to 2n. Does that? It sounds correct, right? So a has to be 1. Am I correct? A has to be 1. How about b? So a is now 1. A is now 1, so this is 2n minus 1. This is 2n minus 2. So b has to be minus 1. Am I correct? Does that make sense? Okay, good. So we get a particular solution. We know that this particular solution will fit this whole thing. So by assuming, by guessing an looks like this form, we get a particular solution. This particular solution is going to be n squared minus n squared, 1 times n squared, minus 1 times n, so minus n, plus c. Is that okay? But for any c, okay, make it 0. Plus c, it makes it 0. Okay? Okay, so we get a particular solution. So this is a particular solution. But still, we need to get a homogeneous solution. So this is the particular solution. And we want to get zeros, the homogeneous solutions. We get the zeros. How do we get the zeros? The zeros ignore anything that is unrelated to the past terms. So we have an is equal to an minus 1. So anytime a, so this a is not the guess a. Okay, anytime a will fit for the zeros. Is that okay? Anytime a will fit for the zeros. Actually, it is like the c that we have, but anytime a for this particular case, because if we ignore this part, we will have an is equal to an minus 1. How can you come up with an is equal to an minus 1? So if an is equal to 1, then an minus 1 is equal to 1, then everything is equal to 1, right? Or an is equal to 2, an minus 1 is equal to 2, then everything is equal to 2, then it works, right? So for any a, it can be a 0 for this particular recurrence relation. So now, at this point, we have a general solution, and somehow, for some reason, this general solution is the only solution that can solve this relation. That can solve this recurrence relation. And then how do we get the answer that fits a1 is equal to 2? So to fit a1 is equal to 2, you plug in n is equal to 1, and then you hope that it is going to be equal to 2. Is that okay? And then so you get what is the value of this a, and then it works. Okay? So if you plug in 1 here, then this will be 1 squared minus 1. 1 squared minus 1 is 0, right? But I want the answer is equal to 2, then what should I do? I need to add 2 there. So this is the 2 that I should have. Is that okay? Is that okay? So that's it. So we have a lot of values computed. Just quickly check. A1, we know that it is correct. It is because we are using A1 to solve this one. So A1 is correct. Let's try A2. Let's check whether it is equal to 4. So 2 squared minus 2 plus 2. So it is 4 minus 2 plus 2. It is equal to 4. Is that okay? And then the next one is 3 squared minus 3 plus 2. It is 9 minus 3 plus 2. This will be 8. And then the next one is 4 squared minus 4 plus 2. So it is 16 minus 4, and then plus 2. So it is 14. So it works. Okay, it works. So, okay, so today, okay, we have demonstrated a very simple example to do this. So this is a strategy for linear recurrence. Guess a particular solution, find the homogeneous solution, combine them together to get a general solution. After that, use the boundary condition to solve for the unknowns that is created during the homogeneous solution. So next time, we will talk about how to find a systematic way to get the homogeneous solution. So the homogeneous solution today, I just talk about, okay, let's try a times minus 1 to the power n. Okay, it works. And here, let's try a. It works, right? Is there a systematic way, an easy way to find out how the homogeneous solution looks like? So there is a very, very mechanical way, very easy way to do that. So we will talk about this what is the day? Today is Tuesday. Okay, good. So we still have a Thursday class. So we will talk about that on Thursday. Okay, and then good luck to the exam. Okay, so next week is the exam. Thanks. Okay.